Okay, and modification means to change. So it's changing from our ancestors. And what Darwin did differently, he came up with this mechanism of natural selection. Remember that these adaptations and those adaptations that are best fit for the environment get selected. But he also came up with the idea of common ancestry. And this was different than Lamarck. Remember, Lamarck showed each of the species had its own lineage, okay? But what Darwin was saying is that all species have a common ancestor. And different species have adapted to live in their own particular environments or their own particular habitats. Okay, and he's thinking again about these mockingbirds. Throughout the course of these 20 years while he's writing The Origin of Species, he's coming up with several different examples other than the mockingbirds or the finches, as he later found out. But what he described, and this gives me goosebumps just talking about it because it's so exciting, he described life as a tree. And this is an actual picture from his book. And what you see up in the top corner, it says, I think. And he's saying, I think life is a tree. And what he's representing here is this tree. Each of these nodes represent a branching point between species. And the tips of those trees represent species. And any tip that has a line through it is a species that went extinct. So Darwin is recognizing that all life on Earth is related, but that a lot of species have gone extinct. And so using the image in your book, I'll turn off the lights here so we can see this. This is what we call a phylogenetic tree of the elephants and their close ancestors, their close relatives. And what we can see is that there's 7 lineages of elephants that have gone extinct in the last 30 million years. Only a couple still remain, the Asian and African elephants. Okay? So we don't see, with elephants, we don't see these intermediates between their ancestors and modern ones, but we can look at the fossil record, and this is what Darwin was doing. He was looking at the fossil record to get an idea of what these intermediates look like. And so now, through reconstruction based on fossils and based on genetic evidence, we know that elephants are closely related to the Saurians and the Hyraxes. The Saurians are the manatees and dugongs, those funny-looking marine mammals that swim around down in Florida. So Darwin comes up with the mechanism, and he comes up with this idea of the tree of life. And this is the mechanism and the model for evolution that we still use today. But Darwin wanted to be sure that he knew what he was talking about and that he was able to articulate what he was saying. So one of the things he did, and remember, he's coming up with this argument over 20 years. 20 years. And what he's saying is that natural selection is the driving force of evolution. Natural selection is the driving force of evolution. The first thing that he talks about, and it's one of the first chapters in his book, I believe it's chapter 2 or 3, is artificial selection. And he uses the idea of breeders breeding things like pigeons and dogs to describe how natural selection works. We have an ancestor in dogs that's the gray wolf. The gray wolf is essentially the ancestor to all dogs. Well, if you look at some species, and here's a very funny example, this pug here looks nothing like the majestic gray wolf of the wild. Okay? But through selective breeding, through man selecting certain traits in the puppies, they could basically create these species. And Darwin's saying, hey, if we can do this in just a few hundred or a few thousand years, why couldn't nature, working over millions of years, do the same thing? Okay? And so he came up with this idea, this principles of natural selection, and he went through a whole bunch of different examples like this in his book, and he comes up with these principles of natural selection. This consists of 2 observations and 2 inferences. The first observation is that in a population of organisms, there is variation. There's variation, meaning not all the individuals are the same. Okay? So there's differences. Observation number 2. More offspring are produced in any generation than can survive. Okay, so there's going to be a struggle. Certain individuals are going to survive. The first inference is that offspring with the best characters survive and reproduce more than those with the characters that are not as good. Okay? Now notice what I say here. Offspring with the best characteristics survive and reproduce more. It doesn't mean that they're the only ones that are going to survive and reproduce. It means that they're going to do so proportionally more than those organisms without the best characteristics. Okay? The second inference that he makes is that there is an accumulation of favorable traits. So through successive generations of the organisms with the best characters surviving and reproducing more, we're going to see over time this population accumulate those favorable characteristics. Okay, so this is natural selection. More offspring are producing than can survive. There's variation in the population. Offspring with the best characteristics are going to reproduce and survive more. And we're going to see an accumulation of those traits, those favorable traits. So one of the arguments for natural selection is this idea of overproduction. And Darwin was influenced by Thomas Malthus, who wrote an essay on the principle of population. And Malthus was talking about human populations, and he was arguing, hey, there's people are reproducing more than we can feed, and there weren't enough resources to go around. But Darwin took that idea and expanded it into nature. And he noticed that this occurs in nature. And one of the greatest examples is salmon. Okay, we've all seen salmon. You've probably seen videos of them laying eggs. Well, salmon lay hundreds and hundreds of eggs, then they die. Okay, in the hopes that 2 or 3 of those individuals will make it back. Right? So only a couple individuals of those hundreds of salmon are going to make it back. And so let's look at some examples of natural selection in action. This is a great example here. This is called the stickleback, this fish here. And the stickleback, this is the 3-spine stickleback. Sticklebacks are found in freshwater, saltwater. They're found in a lot of different places. Some sticklebacks have these plates, and here these are 3 stained fish, and the plates are stained in red. And these plates offer them protection, but they're very cumbersome. So if they don't need them, it's better not to have them. And so what they found is, here's a lake here, and up in Lake Washington, there's a great study that what happened is in Lake Washington, there's a bunch of nutrients being washed into the lake. And what that did is it made it very cloudy. Okay, there's big algal blooms, and it made it very cloudy. And so these sticklebacks were hard to see by the trout that lived in that lake. And so the sticklebacks evolved over time to have fewer plates, because remember, having plates is cumbersome. And they didn't really need them because they weren't being preyed upon very much by the trout. Well, there were some legislative efforts in Washington and Seattle that to curb the amount of nutrients going into that lake. And what happened is over time, this lake got much clearer. So now the trout are a problem. And what they found, the scientists found that after the lake became clear, the sticklebacks evolved to have the plates again. So what that meant was that in those populations of sticklebacks, there were some that had plates and some that didn't. And over time, the plates were selected for. That's natural selection in action. Okay? Here's another great example. The eastern fence lizard, Scoloporus undulatus. Okay, Scoloporus undulatus is this species of lizard. I'm sure you've seen the western fence lizard. But fire ants were introduced into the United States in the early and mid-1900s. And what we can see is, over time, in these areas, as the fire ants start to invade the range of this lizard, is that their legs start to get longer. Well, it turns out that the lizards are using their legs to knock off the ants. And having longer legs is favorable because they can knock off the ants on more parts of their body. And so what we see is in the areas of intense fire ants, we see lizards with much longer legs. And so these are some great examples of natural selection in action. And here you can see the graph showing what we're showing here on the x-axis is generations or time, and on the y-axis is basically the relative length of the hind limbs. But what you can see is through time, these limbs get bigger and bigger. And so this is a great example, and there's thousands of these in action. And next time we come back, we'll talk about how natural selection works in a desert mouse population. And you guys have all had some bit of genetics. We'll talk about how natural selection working on the phenotype will then relate to the genotype.